Thank you very much. I'm happy that we were able to have this seminar in an online edition in 2020. And today my work talks about how can we think about interventions over time, so on a time to event, and to understand how these interventions can reduce health disparities in cancer outcomes. So this is joint work with Hélène Jacquemin Gadda and Cécile Proust-Lima at the University of Bordeaux, so from your school. And I really enjoyed working with you in the past years. So this has been a long project with a lot of interesting both conceptual, public health, and methodological interesting points that I hope I will be able to walk you through today. And also my longtime collaborator, Jarvis Chen, who actually introduced me to the field of health disparities research when I was a postdoctoral fellow at Harvard University. And so I want to acknowledge him as well. So why I became interested in the field of health disparities? Definitively, it's a critical still gap in national health institutes and a big priority for them to identify, monitor, and potentially implement public health interventions to reduce gaps in survival across the racial ethnic continuum as well as the income continuum. My expertise in causal inference, I hope, can help to identify the causes of these observed disparities. There are two methodological challenges that really fascinate me in studying this question. So cancer is a very complex disease that has a long latency period between the onset and the development of its symptoms and eventually its clinical diagnosis. And then I would say that there is a critical moment from clinical diagnosis to death, and that's where the patient enters the clinical system, the hospital. That's when it can be cared, and that's where it's really important that we do all we can to improve their survival. However, we know that racial disparities can, occur even before clinical diagnosis presents. However, in this talk, I will mostly focus on what we can do to reduce these disparities after the patient is diagnosed with the disease. And in particular, how better and timely treatment decision-making and equitable treatment decision-making can help reducing racial disparities in cancer survival. Our motivating application comes from the field of colorectal cancer, which is one of the most common cancer in the United States, that unfortunately still now demonstrates widening mortality disparities between whites and blacks. So in this talk, I will also focus only on the dichotomy between white patients and African American patients. However, there are known differences also between whites and Hispanic and Asian patients. However, we don't have enough sample, we don't have enough data on these other ethnic minorities to study these disparities well, but they are there. Prior work, both based on the US as well as the UK cancer registries, identified income as well as differences in stage of diagnosis as important in explaining some of the differences that we observe in survival between people of different incomes as well as people of different races. However, employing causal inference approaches, we understood that potentially the role of stage of diagnosis might have been overestimated. That is, prior work showed that African American might have displayed no difference in survival between with whites had to intervene on stage diagnosis. However, in our work, we found that is only 30% of these disparities that can be attributed to stage. And this discrepancies is mostly to be accounted by the way we adjust for confounders. So prior work did not appropriately adjust for confounding. And another important issue is model misspecification. That is, most of the models that were used to study interventions on stage or screening assumed linear models, whereas as we see in our application, there are many non-linearities in this data, as I will discuss later. There is also research showing that once the cancer is diagnosed, quality of care differs by income. And in particular, the focus of this talk is about disparities in timeliness of care, where I define timeliness of care as the rapid initiation of treatment after a definitive diagnosis. In the Seer Cancer Registry in the US, several scholars identified differences across racial ethnic groups in timeliness of care. And this is actually for many of the cancers, breast, prostate, and lung cancer, along with colorectal cancer, where Black patients were more likely to experience delays in care. As I mentioned before, when we model, we want to try to understand disparities in timeliness of care, disparities in survival. We need to recognize the complex cultural, geographic, and socioeconomic context that shape these health disparities. That this is not only a matter of race, it is a matter of the context where the person also lives. And that has to be taken into account in our modeling procedure. So what is the scientific question that we set to address and develop novel methodology at this purpose? We wanted to understand whether if we were to intervene, eliminating differences in time to treatment, in distribution, such that the more disadvantaged groups were observed to be treated as timely as the more advantaged groups, then how much would we be able to reduce disparities in survival? So the premise is that we observe racial differences in survival for a certain cancer. And our question is, what if we could change the timing at which the African American group, which is the group that experiences the least survival, what if we reduced their delay in treatment such that they are treated as timely as the whites? Would this reduce, this reduction in the delay of treatment improve their survival and also reduce the gaps in survival between white and Black? So formally, this corresponds to a type of direct effect. It's a direct effect because we are looking at the difference between Black and white in survival when we fix an intermediate factor, which happens to be a time to event factor. It's also a stochastic intervention because we don't attempt to fix the time to treatment to be the same for everyone. We are instead attempting to change its distribution. So that's why this is a stochastic intervention. This is a visual representation of the intervention that we seek. Here we observe the Kaplan-Meier curves for the time to surgery, which is the first line of treatment for colorectal cancer patients, stage 1 to stage 3. And we observe two curves. The blue curve corresponds to the waiting time to surgery for Blacks, and the red one for whites. As we observe, the red line is below the blue line, indicating that whites have a shorter waiting time for surgery, which is good you would want to be treated earlier, if possible. What we would want to do is, what if the two curves matched? What if we were able to intervene so that there was no difference in these two curves, and the two curves matched the red curve? So methodologically, what is the estimand that we care about? As I said, the type of estimand is a type of direct effect. So before setting up doing this work, we delved into the literature search, and we actually found out that very recently a lot of methodology arose to study the potential effects of competing risks in causal inference. And this is highly relevant to us, because whenever we try to intervene on a non-terminal time to event, in this case, time to treatment, there is always the risk that some patients did not experience the intermediate time to event, did not obtain the treatment because they died prior to receiving treatment. So this is an issue that is also called truncation, and is a distinct phenomenon from censoring. So censoring happens when a person has a time to event that is not observed, because they either the censoring is administrative or it's because they leave the study. Here, the intermediate factor, if they die, is not even defined, because the person dies before receiving the treatment. So recently, several authors have considered how to study mediation in the context of survival analysis and when the outcome is truncated. However, none of this prior work considers the intermediate non-terminal event as a time to event. So that's how we fill the gap in the literature. So I would like to introduce some notation before formalizing the causal contrasts. We denote R as our exposure of interest, which is racial ethnic status, that for us is going to be binary, black or white. X is a cancer stage at diagnosis, which is is a key variable in cancer, and actually all our analyses are going to be stratified by stage, because depending on your stage, you're going to have a different treatment protocol. So different reasons why you should be delaying treatment. For example, it's clear that stage 4 patients are gonna less likely to experience a delay in treatment, but also their primary treatment is different from the treatment that the stage 1 to stage 3 patient would receive. So it's very important to consider each of the stages separately. We denote with T a waiting time to first line of treatment from diagnosis in months, which is a non-terminal event process. With S, we denote survival time, which is a terminal event process instead, and K is a censoring time. We denote with YT and YS respectively the last observation times for the non-terminal event process, time to treatment, and S, which is the terminal event process. Delta T and delta S are the event observation indicators, and C is a vector of potential confounders of the relationship between time to treatment and time to death. We denote with OI our observed data. This is the directed acyclic graph that represents our study. So we have our racial ethnic status factor that is going to affect both stage, time to treatment, and survival. And then we also have covariates C that affect stage at diagnosis, treatment status, and time, and the survival. I now also introduce our potential outcomes. So with little g, we denote a fixed or stochastic intervention. As I said, here we are interested in a stochastic intervention, whereas G is defined as a function, is a function G, T, X, C, R, which is a random draw from the time to treatment distribution observed for individuals with race equal little r, stage equal little x, and C equal little c. So thinking about that, this G could be whatever function we want. It could be an exponential, it could be a y-ball, but in this case, we decide to consider this as being the time to treatment distribution as observed in the group that has race level equal r, x level equal little x, and c level equal little c. So we will have to estimate this G, okay? But that's not doesn't have to be the case. We choose to estimate it from the data, but we could also set it as a synthetic variable that we generate from our computer. We denote S subscript G a potential survival time if, potentially contrary to fact, the time to treatment was randomly drawn from the distribution little g. So given this notation, we can define the objects we are interested in estimating, non-parametrically for now. We call these objects DS and RDS, where D denotes the disparity, which we define on the survival probability scale. In particular, this is the difference in the probability of surviving after time little s in the racial group equal 1, the blacks, relative to the whites, r equals 0. So this is our observed disparity. And then here comes our causal contrast, that is the residual disparity, RD, under intervention G, which is the disparity, again, on the difference in the probability of surviving after time little s between black and white, if we intervened setting the time to treatment distribution to little g. So after we have computed these two causal contrasts, we can also get the proportion of the disparity that would be eliminated under the intervention little g. Now, let's look at these two objects. The first object simply describes reality. So this is an association. It's a pure association for which we just need to model correctly these relationships to get it right. For the second one, that involves a potential value. So we need additional assumptions to be able to identify non-parametrically this object. So what are these assumptions? The first assumption is the one of consistency, which indicates that the potential value of surviving after delivering intervention little g that realizes in a time to treatment equal little t is exactly equal to the survival time in the real world where we observe a person actually treated at time little t. That, for example, means our intervention that leads to a reduction in the delay is exactly the same as delivering the treatment in real life. We are not doing anything different than what would be done in real life. Conditional exchangeability is the assumption of no unmeasured confounding of the time to treatment survival distribution, conditionally on race, stage, and the other covariates. We also assume positivity, which indicates basically that we are not extrapolating from our data. That is, for each levels of race, stage, and baseline covariate such that their joint density is greater than 0, then the probability that the treatment time will take a value little t given those values of R, X, and C, it has to be greater than 0 with probability 1. And then potentially this assumption could be relaxed, but for now we also assume non-informative censoring. So under these assumptions, our causal contrast, the residual disparity, can be rewritten as functions of observed data. And as I write here, the interpretation of this non-parametric estimator is basically the standardized difference in the survival probabilities between black and white conditionally on time to treatment, standardized over the density of time to treatment among the whites. So how can we operationalize this non-parametric estimator and actually get estimates? So we know that there is the course of dimensionality, so it's really challenging to estimate this object non-parametrically. So we resort to modeling, and that's what we will do. But before thinking about the models we want to fit, let's understand better how this estimator behaves. What are the components of this estimator? So to understand that, we denote with P delta S delta T S given R, the joint probability for the survival and treatment status at time S for the racial ethnic group R. To recover the quantity ds, what do we need? We need to estimate the following probabilities. For the least disadvantaged group, the whites, we need to know what's the probability at time S to be alive and untreated. That's why we now call this P underscore 0, 0, because if you are alive and untreated, your delta S is 0 and your delta T is 0. And we are saying we want to do this probability at time S, so that's why we have an S there, among the whites, so that's why we have a given 0. So similarly, we can define the other probabilities, that is the probability to be alive and treated at time S. And then the same we do for the African American group. That is, we want to know, given that you are an African American at time S, what's your probability to be alive and untreated, and what is your probability to be alive and treated. In addition to these probabilities, in order to recover the residual disparity, we need to learn additional 2 probabilities. That is, the probabilities of being alive and treated or untreated under the intervention G. So how does that change? We will now need to estimate the probability to be alive at time S for the African American group, but also when this group is untreated at time S as observed in the white group. So that's why now we write a P underscore G 0, 0, because now we have intervened on the probability of being untreated at time S by changing what we actually observe to an hypothetical scenario. Similarly, we want to also know what's the probability to be alive at time S for the African American group, but also treated for that group at time S as observed in the R equals 0 group. So now combining these terms, actually the estimator for the disparity measure ds is given as a function, a combination of these probabilities, as well as the estimator for the residual disparity. So let's think about how we can actually estimate these probabilities. Actually, each component of the residual disparity and disparity estimators can be expressed as function of the hazard and the cumulative hazard functions, where here I'm highlighting in red those components of the estimators that involve the intervention. So as you see, after we have actually decomposed all the components, maybe this formula appears kind of complicated. That's part of the proof that we have. That is, after you know what are these probabilities, then you can just relate them to the hazard and cumulative hazards, which we know is very easy to model, say, with the Cox regression. So again, what's the interpretation now of this estimator? Let's focus on the residual disparity. We can interpret this as the difference between the global survival of a Black in the counterfactual world, in which Blacks colorectal cancer patients have the same time to treatment distribution of Whites colorectal cancer patients. And we compare, this probability in Blacks with the global survival of a White patient. So in order to estimate these survival probabilities, we leverage the illness-death model representation of our problem. So effectively, our cancer patients enter in the study when they are diagnosed. We call this stage 0. And then two things can happen. They either transition to a treatment stage, which is for us called the stage 1. And I have it here in red because that's where we want to intervene. That's where intervention works. We are trying to change the intensity of transitioning from 0 to 1. And then from treatment status, they can transition to death status or they can be censored. Alternatively, patients can transition from diagnosis to death. And this is where the semi-competing risk nature of the data arises. Alternatively, they can just be censored. That is, we neither observe their treatment status nor their death status. They are untreated and alive at the end of the study. So each of these transitions can be modeled, as I show here on the left side of the screen. And we have a model for the hazard for transitioning to treatment as function of the race variable, stage variable, and covariance. We have a model for transitioning to state 2, which is the death status, again, conditionally on race, stage, and covariance. And then we have the modeling for the intensity of the transition from treatment to death, where we furthermore allow for a covariate being our actually time to treatment, with the idea that the hypothesis here is that waiting for treatment too long might be harmful, might actually accelerate your transition to death. We actually find that it's very hard to model this relationship because, as you can imagine, it's highly affected by confounding, because there are two reasons why your treatment is delayed. The one that started all this study because you're disadvantaged, you experience discrimination, and so your treatment is delayed, or is because you're doing well, you are healthy, and that's why you wait longer to get treatment. And that's the confounding issue, how to adjust for latent health status. That's one of the main challenges. So there are also alternative estimators that or estimates that we can be interested in. I have it here, but I just would like to move forward because it's just a modification of the primary causal contrast of interest. I don't want to confuse anyone. So actually, I think I have, sorry, I missed one slide that is very important. So after we have decided that, say, we have a model for the hazards of these transitions, now how do we actually operationalize this semi-parametric estimator? So it's very natural to choose the multistate model as the model for these transition hazards. And there is the M-state R package that we can use at this purpose. So the first part is actually trying our best to model the relationship between all these covariates and each of these transitions. And the next step is to actually estimate this integral. So there we see that this racial disparity estimator involves the estimation of each of these probabilities that involve integration. So what we do is that after we have fitted the multi-state model, for observed times in the range 0 to S, we predict the baseline hazards, cumulative hazards for each transitions, and for each racial ethnic group, and time to treatment. And then we estimate the causal effects of interest by plugging in the estimated hazards and cumulative hazards and computing the integrals. And then we conduct this procedure within a bootstrap resampling to obtain uncertainty around our estimates. So actually, the most challenging part of this project was actually to derive the estimators and understand how we can leverage the illness-death model to make it fit in this causal inference framework. But the implementation is pretty straightforward. So I will conclude the talk just showing you a preliminary analysis of an application of this methodology in a cohort study, the Cancer Care Outcomes Research and Surveillance Consortium, that was actually established to study quality of care across racial ethnic groups in lung and colorectal cancer patients. So this is a study that enrolled from 7 research medical hospitals, patients between 2003 and 2005, and the geographical locations of this hospital matched the SEER cancer registry in the US. And the reason why we decided to use this cohort study is because there was information on health status, socioeconomic status at the individual level, as well as treatment regime. Our analysis included about 1,600 non-Hispanic white and non-Hispanic black who had colorectal cancer as their first diagnosis. Here is again our tag, where I now indicate that our X includes not only stage of diagnosis, but also age at diagnosis, income, insurance status, medical center, and type of cancer. Whereas gender is the only baseline confounder we have, because all the other confounders are actually affected by race. So this is how the Kaplan-Meier curve look in our data for including everyone and just comparing African Americans and white. So we observe racial disparities in survival, whereby African Americans unfortunately die early. And we see the figure I showed you before, that now whites get treated earlier than blacks. So the question is, if this is the picture, we see that African Americans get a delay in care and they also die earlier. Is this earlier death attributed to a delay in treatment? This is the scientific question. Can we reduce these disparities by eliminating this time to treatment disparity? This is the policy question. One other thing that I wanted you to notice is that in this application, the problem of semi-competing risks is not huge. Is 7% of these colorectal cancer patients die before receiving treatment. This is the plot that shows the overall results of our analysis, where the blue line indicates the disparity in survival between black and whites, and in the x-axis we see each month, and the green line indicates the the green line indicates the disparity, and the blue line indicates what's residual after the intervention. And we see that after intervening, at 24 months, say from the diagnosis, the disparity would be slightly lower than without the intervention. So this indicates that we would have a minimal reduction in the disparity if we were to intervene on time to treatment. And there might be many reasons why that's the case. So first of all, I would like to indicate that in this population, we don't see a strong racial disparity. First, it's only about 0.09 difference in the survival probability, indicating already a small racial disparity, albeit statistically significant. And the other reason why we might not see strong changes is that, albeit we see a significant disparity in delay, that's not very large. So one of the, I would say, the main limitations of this application is that the CanCORS analysis includes only medical centers. So if it only includes medical center, then means, medical centers are also research centers with high quality of care, which indicates that maybe this analysis might not be representative of what's happening in the US population in general. So this is a subgroup of the population that gets high quality of care. But there might be other things that we might improve in our modeling. For example, we might have unmeasured confounding. So it's likely that adjusting for residual unmeasured confounding, this small disparity reduction might even go away because we might have unmeasured confounding. Another issue is measurement error, because in this data, time to surgery is self-reported, and there might be error in reporting. Again, and this could bias results in either way, could either lead to an overestimation or an underestimation. So in conclusion, we proposed estimates and semi-parametric estimators to evaluate the impact of stochastic interventions on intermediate, censored, and truncated time to event variables. This estimation strategy leverages the illness death model that naturally models semi-competing risks for proper inference and avoids issues of model incompatibility that would arise by separately modeling mediator and outcome. And I see a lot of interesting directions for future research. That is, the first interesting direction would be to allow for time-dependent confounding within this framework, and also allow for multiple sequential treatments, such as not only, say, time to surgery, but also the overall regime of chemotherapy and surgery that cancer patients go through. And also, of course, this approach can be used well beyond the cancer realm, as well as the health disparities research, and be used in any question that arises in epidemiology in a life course perspective, where interventions are taken in continuous time. Thank you for your attention, and I welcome any question.
Thank you very much, Linda. So are there some questions? You can raise your hand, or you can unmute your mic.
Yes.
Maybe you could. So since this illustration in colorectal cancer, you did simulations. Could you maybe give some insights about well, the problem in simulation and how you can compare with existing methods?
Yes, that's a good question. I didn't add it because we haven't really fully finished the simulation, so I wanted to, but I definitely happy to discuss.
Yeah, but between us, it's in the lab.
Yes. So first of all, what are the ways that people right now could be dealing in a naive fashion when you are in the presence of semi-competing risks? The first way is ignoring that actually when you die before receiving treatment is a truncation event, and you treat it as a censoring event. So what that implies is that basically one would indicate the event that the person dies before as a censoring event. You would effectively fit your multi-state model, but then consider the transition from 0 to 2, which is the transition. Let me go back to the illness death model. You would ignore the multi-state nature of your problem, and you would basically ignore the lambda 0-2 terms in your analysis. You would not take into account the modeling of the transition from diagnosis to death. The second alternative way, which is I think the worst, but that unfortunately people might be doing, is simply selecting for their study only the patients who are treated. That is, you select, in other way, you exclude the patients who die before receiving treatment. So based on these two alternatives, and what would be the implication of that? That when you go ahead and fit the multi-state model, your 0-2 transition component are all NAs, because you don't have anyone who happens to enter in that transition, because you have eliminated effectively those patients. So what we did was to simulate synthetic data, assuming that you can have either no semi-competing risks at all, or you have either 10% of the patients that go in the 0-2 transition, or 40%. So the 10% case is the one that mimics more our application. And even in that scenario, that is when you only have 10% of the patients that experience the terminal event before observing the non-terminal one, even then you can severely bias your estimates of the disparity and the residual disparity. So definitively the simulation showed that it is very important to be able to account for the truncation event appropriately. That is you cannot pretend that it's just censoring and treat it as, outside the illness death model representation, basically. We also consider the cases in which we have non-linearities in our data, such as exposure-mediator interactions, to show that, also when you have models that are more complicated, that allow for the racial, ethnic disparity to be different depending on the waiting time for treatment. Even in those scenarios, we see even larger biases. And you will need a larger sample size to be able to detect these effects. Because the model is more complicated. Apart from that, I think that's what's striking, that if you use alternative approaches, you are gonna get bias, even with small semi-competing risk problem. Hélène?
Yes, but I think Virginie had a question also. No?
Another question?
Yes, thank you, Linda, for this. Hello, thank you for this very nice presentation. We have Quentin, which is a PhD student, is working also on a related topic on surrogacy and mediation analysis. And my question is about the assumptions that you make when you publish on causal inference on this kind of topic. Do you have to verify all your assumptions, or you assume that in your context you can assume that they are all verified, as the conditional exchangeability, for instance, or when it's not so easy to prove this? How do you do in practice when you publish? Do you have to spend some time to verify this or not?
So there are some verifiable and some not verifiable assumptions, first of all. So let's go in order. For the consistency assumption, that's not verifiable, but you can define your study so that you are that's closer to be the truth. For example, if I said time to treatment in general, one could say, what treatment? Because it can be whatever, right? And that would violate the consistency assumption. The consistency assumption is very related to, you need to have a very clear intervention in mind. The better that is defined, the closer the consistency assumption is going to be. That's why we actually specified that this is time to surgery. And we said that this is the time to the first line of surgery. It's not like whatever surgery. It has to be the first. So you see, like, because then it's not clear what is the effect you're defining. The conditional exchangeability is an untestable assumption, but we can do sensitivity analysis to test whether, if potentially we had an unmeasured confounder, how much our analysis would change. So definitively, there are a lot of tools to do this sensitivity analysis, so that people are encouraged to do them. The positivity assumption, that's also the reason why I highlighted that it's important to do this analysis by stage. Because if, say, for stage 4, your recommended treatment is chemotherapy, you have a violation of positivity, because I define my treatment as surgery. So if you have a 0 probability that the person in cancer stage is going to have surgery as the first treatment, then I'm violating the positivity assumption. Again, this is a design point, because I have to be sure that the way I'm defining the treatment is such that everyone in the sample that I'm considering has a positive probability to get that treatment. Now, there is another aspect that is more a sample property, which is overlap. That is, we can actually check in our sample that we have a positive probability for everyone in our sample to receive surgery in the time to treatments that we care about. So it's much easier to check visually positivity when you have a binary indicator for your factor. Here is a continuous, is a time to event. So it's a harder assumption to check. But is the sample property of positivity that is called overlap can be checked in the data. So these are the key assumptions. Non-informative censoring can be relaxed. It's not necessary for identification. It just makes it easier for us to identify it, and we don't have to further account for like missing with, thinking, we are basically assuming that this is like missing data that is completely at random. If we made missing at random or missing not at random, again, we could adjust for it.
Thank you.
Mm-hmm.
Thank you very much, Linda. So this time again, this was a very, very clear, very good presentation.
Thank you.
My question was also about this assumption, because I have the same question about how to check that they are valid. And the other point is which of them are the most important and the most susceptible to induce bias. And again, we have already discussed that, but the conditional exchangeability, I find it's not easy to understand, because this is an assumption of independence between the observed time to treatment and the survival, assuming we intervene on the time to treatment. And really, I don't understand intuitively what it means.
Okay, first of all, I mean, this assumption is like saying that your treatment is binary. yes or no. You take the treatment, yes or no. And your potential value under a counterfactual world where you are treated, yes or no, is independent of this assignment. So what's the easiest way to understand this is thinking that we want to identify the true causal effect of delay of treatment and surviving, right? So let's go to our DAG. We want to identify this arrow. We want to estimate the effect of T on S, okay? And the counterfactual thinking tells us, you know, the definition of this effect, of this arrow, if we want to write this arrow in mathematical terms, that's the potential value of S for me, say, what is my survival time? Well, sorry, my death time, let's say, if my treatment level is, say, 1 month, I get treated 1 month after being diagnosed, and I save that value, compare with my time to death, if potentially contrary to fact, I'm not treated at month 1, but I'm treated at month 6, after 6 months that I'm diagnosed, okay? Now, we want to isolate this effect. The survival, on average, for people, if they all get treated at time 1, say, relative to if they all get treated at time 10, you know, waiting 10 months from diagnosis. We don't see this. We only see a group of people who is treated at month 1 and a group of people that is treated at month 10. We know that there might be reasons why some people are treated at month 1 and why some people are treated at month 10. These reasons have to be wiped away. We don't want them to be in the way because they are going to confound this relationship. So basically, this assumption means I'm going to adjust for variables, all the variables, such that the group of people now in this new analysis that adjusts for all these variables, the group of people conditionally on this variable that is treated at month 1 is exchangeable with the group of people that is treated at month 10. That's what this says. Because the potential value, so S subscript G, is not an observed value. It's actually a pre-treatment status. You have to think about that as being a pre-T status, our T, right? Let me go back to the... This
Okay.
S subscript G is the potential value. It's like is a pre-treatment status.
Okay.
I also explained that if you have the recordings of the class I taught in December, I explained this there, if you want to go back to those.
Thank you.
Sure.
I don't see another question.
Just.
Oh, yes.
It's hi, Linda. This is Karen.
Hi, Karen. How are you?
I'm good, and you?
Good.
I've just a naive question about your final results in the application. So you find 40% for the proportion of disparities eliminated by the intervention. That's it?
Not significant, yeah.
Yeah, but this, because we are in a survival analysis setting, I guess that these results depends on the length of follow-up, no? And
as we see, yes, I mean, as we see let me go back. As we see, actually, these effects change over time.
yeah, so when you say 40%, at which time does it correspond?
At 24 months.
Ah, yeah, okay.
Yeah.
Okay, and so if you look at 60 months,
That's
for example, you don't have any...
no difference, but you know, what I would focus on, Karen, is really looking at the confidence intervals. They are completely overlapping. Basically, this indicates that there is no real difference, like, between the disparity and the residual disparity. You see? Like, if we consider the uncertainty that we have around these measures, we know that there is a significant disparities at 24 months, but the residual disparity is, you know, basically almost completely overlapping the confidence interval. And this 14%, again, I haven't pasted so I don't show confidence intervals for this proportion measure, because many times this proportion measure, especially if it's close to 0, it gets pretty unstable and you can get very wild confidence intervals. So I think what's more revealing here is to see that, yes, the residual disparity is slightly lower, but the confidence intervals almost completely match, indicating that the conclusion here is that this intervention in this sample doesn't show that the delay of treatment is an important determinant. It's actually not very important. That's what we see in this sample, which, yeah, does this answer your question?
Yeah, sure.
But again, I wouldn't generalize beyond this sample, because I don't think that this group of patients is representative of what's happening in community hospitals or, you know, less quality hospitals that are around the United States. These are all, UCLA, Harvard, like these are all hospitals with very high quality of care.
And in your simulation, did you control for this effect, or are you able to fix the effect, or the true effect? I mean, you calculate it from the model that you generate, but you are not able, I guess, to fix it, or is it possible?
You're asking me how we are doing the simulations. So for the simulations, we have a formula here. So basically, the true effect is computed by, we know by simulation what these lambdas are. Let's say we generated based on a y-ball distribution. So we specified the shape, the location, and the scale parameters. So once we know them, we know the lambdas. And so once we know the lambdas, we know what these objects are. So that's how you compute the truth. Does this answer your question?
Yeah.
So it's almost time. So I think we will finish here. Thank you very much, Linda. That was a great talk. It's a great work also. Well, I hope next time you will be able to come to Bordeaux to show us the end of this work and maybe some extensions. But well, yeah, next time. So thank you very much, all of you, and have a nice end of afternoon and a nice day.
Thank you everyone for joining and for inviting me. Have a good summer, everyone. Bye.
Thank you, Linda.
Thank you.
You too.
Thank you. Very nice.
Thank you.
Bye-bye.
Bye.
Bye, Linda.
Very nice talk.
Thank you. Bye.
Bye.